In the last lecture, we started looking at symmetries of the scattering matrix. Or to be more precise, the consequences that symmetries of a system has on the scattering matrix elements. Our subject in the last lecture was continuous Poincare symmetries of a system. That is, symmetries which tell you what happens when you go from one inertial frame to another, and which, according to the principle of special relativity, happens to be a symmetry of all physical systems. In today's lecture, we are going to take a look at internal symmetries. These are symmetries which have nothing to do with the Lorentz invariance of a system, and in particular, looks the same irrespective of which inertial frame you are looking at. And examples include things like isospin symmetry, charge conjugation symmetry, so-called global U1 symmetry, the symmetry in which you change the phase of a system by a constant global amount, and so on. Now, just like a Poincare transformation was implemented on a Hilbert space of states by the action of a corresponding unitary operator, a similar thing also happens here. An internal symmetry T acts on the Hilbert space of physical states in the form of a unitary operator U of T. And this U of T induces a linear transformation on the indices labeling particle species. This is what is different from Lorentz transformations or general Poincare transformations. In general Poincare transformations, the labels which describe the system that are affected are the momentum and the spin labels. The third label, the labels describing a particle species, was the same before and after a Lorentz transformation. Lorentz transformation, of course, does not change the identity of the particle. On the other hand, when we have things like, say, the isospin symmetry, which might change a proton into a neutron and vice versa, what happens is the action is on these labels which talk about what the particle is and not on the momentum or spin labels. In other words, U of T acting on a state psi described by a bunch of labels, P1 sigma 1 n1, P2 sigma 2 n2 and so on, basically produces a linear combination of states with the same momenta, same spin components. So P1 sigma 1 is the same on the left and the right, but a combination of different particle species labels. So N1 prime, N2 prime and so on. These are the things that change. And of course the linear combinations need coefficients, and these coefficients form matrices. Curly D N1 prime N1 is the N1 prime at N1th element of a matrix curly D of T. Similarly, this is the N2 prime N2th element of curly D of T. And since we know that two transformations carried one after the other, T bar T, which means T bar after T, must have the same effect as doing them in one go, U of T bar T must be the same as U of T bar times U of T. In other words, U's form a representation of the corresponding symmetric group, and as an immediate consequence, the matrices curly D's also obey the same composition rule. Curly D of T bar times curly D of T must be curly D of T bar T. Another important consequence that follows immediately from the fact that U of T is a unitary operator is the following. If you take the inner product of two different particle states with different particle labels, P1 sigma 1 N1, P2 sigma 2 N2 for one, P1 bar sigma 1 bar N1 bar, P2 bar sigma 2 bar N2 bar for the other, this particular inner product must be the same as the inner product that you get when you apply U of T on both of these two states. That's simply a consequence of the fact that U of T is unitary. And just by using the fact that U of T acting on P1 sigma 1 N1, P2 sigma 2 N2 is going to be a linear combination over N1 prime, N2 prime and so on of the states psi with labels P1 sigma 1 N1 prime, P2 sigma 2 N2 prime with coefficients curly D N1 prime N1 of T, curly D N2 prime N2 of T and so on. Of course, there's a conjugation here because of the fact that the inner product is antilinear in the first factor, and similarly the u of t acting on this state, p1 bar, sigma 1 bar, n1 bar and so on, gives you curly d n1 bar prime n1 bar t, curly d n2 bar prime n2 bar t and so on. No conjugations here because of course the inner product is linear in the second factor. Now, we know the inner product for such multiple particle states is basically a product of the individual inner products for single particle states along with contributions from possible permutations of particle labels, and you have delta cube of p1 vector minus p1 bar vector. These two momenta, at least the three momentum part of these two have to be the same. Then delta of sigma 1 bar, delta of n1 bar and so on. This is for the left hand side. And the consequence of the unitarity becomes this following relationship which the matrix elements curly d, n1 prime, n1, etc. must obey. There is nothing but the right hand side of this expression written down with the inner product written down explicitly. Now, because this has to be correct no matter what the momenta etc. are, the relationship basically is one between the particle species label. So, what you ultimately end up with is delta n1 bar, delta n2 bar, etc. This product must be equal to this product of the curly D matrices, the conjugates coming from the first wave vector and the values themselves coming from the second wave vector. Times these, which are the corresponding delta symbols which come from the inner products here. This delta n1 bar, n1 prime bar, this delta n2 prime bar and so on. Just realize that what we have done here is we have just written down this expression all over again. Just the particle species dependent portions, this, and these of course depend on the particle species and these factors. The other factors which depend on the momentum, because this has to match for all p values, all sigma values and so on. Now we use these delta symbols on the right hand side to simplify this expression considerably. You have sums over n1 prime, n2 prime and so on, and also over n1 bar prime, n2 bar prime. These were the labels for the second state, or at least the transformed versions for the second state. Now, because of the presence of these delta symbols, what we can do is we can trivially sum up over n1 bar prime, n2 bar prime and so on. And of course, what that is going to do is replace all these n1 bar primes by n1 prime, n2 bar primes by n2 prime and so on. And so, this summation essentially becomes a sum over n1 prime of curly d star n1 prime n1 t coming from this term times curly d of n1 prime n1 bar of t, where this n1 bar prime has been replaced by n1 prime because of this summation over n1 bar prime. And similarly, we have another expression for with n2 primes summed with a sum over n2 prime and so on. Now, once again, on the left hand side, there's only one factor which depends on n1 and n1 bar. And on the right hand side, the only term which depends on n1 and n1 bar is this one. All the others are independent of n1 and n1 bar. And a similar statement can be made about n2 n2 bar. The only term which depends on n2 n2 bar is this one. On the right hand side, this is the only term which depends on n2 n2 bar. So each of them must be individually equal. That is, this term has to be equal to this delta. This sum must be equal to this delta and so on. An immediate consequence of this will be, we can write all of these together as a single equation basically, sum over all n prime. So what was n1 prime, n2 prime, etc. separately there, I'm just calling n prime now. Curly d star n prime n t and curly d n prime n bar t must be delta n bar. This works no matter whether n is n1, n bar is of course n1 bar and so on, or n is n2 and n bar is n2 bar and so on. This is of course nothing but the statement that the product of d dagger, the matrix, and d must be the identity matrix. And therefore our conclusion is the representation matrices curly D for an internal symmetry must be unitary matrices. So curly D dagger T must be curly D inverse of T. Now that we have seen how states would transform under an internal symmetry transformation, let us see what consequence this has for the scattering matrix elements. Recall that a scattering matrix element given by S of P1 prime, sigma 1 prime, N1 prime, P2 prime, sigma 2 prime, N2 prime for the out state and P1 sigma 1 N1, P2 sigma 2 N2 for the in state is nothing but the overlap between the in state with particle labels P1 sigma 1 N1, P2 sigma 2 N2 and so on, and an out state with particle labels P1 prime, sigma 1 prime, N1 prime, P2 prime, sigma 2 prime, N2 prime and so on. Now, because of the fact that U of T is unitary, we can of course get the same result by applying U of T on both of these states. And if you do that, each of these transform according to the same rule that we had written down before. The curly D's are nothing but representation matrices for the symmetry transformation T. As you have just seen, they are unitary matrices. And just a word about the notation. What we have done here is we have talked about the incoming particle labels as those without primes, and the primed ones are of course the outgoing particle labels. Here, once you have applied U of T on both of the incoming and the outgoing particle states, you are going to get a linear combination. Remember, linear combination with the same moment and spin components but different particle species labels. And we have just used bars on top of the particle species labels here. So, what happens when U of T acts on psi minus pi, P1 prime, sigma 1 prime, N1 prime, P2 prime, sigma 2 prime, N2 prime, etc. is a combination with these as coefficients, and the sum is over particle species labels which we have called N1 bar prime, N2 bar prime and so on. Similarly, for the incoming particle states which had particle species labels N1, N2 and so on, you now have a combination where the particle species labels have been replaced by N1 bar, N2 bar and so on, and you are going to sum of course over all N1 bar, N2 bar. The N1, N2, the original particle species labels of course are still there as one of the indices of the matrix elements. Now, using the fact once again that an inner product is antilinear in the first factor and linear in the second, can simply take out all these matrix elements, and this will end up with a sum over conjugates of the products of these things and a sum over N1 bar, N2 bar of these elements directly times the inner product of this with this, which is of course the S matrix element with these as our particle labels. Particle labels, remember, include both the particle momenta and spin values as well as the particle species labels. And as far as internal symmetries are concerned, it's really the particle species labels which interest us, because the particle momentum and spin components will not change under such a transformation. They're the same on both sides. Now, there's one very important thing which I took for granted here, which is you're applying a U of T, a unitary operator, on both of these states. And the action of U of T on both of these states follow the same basic pattern. Now, this happens only if you have the same bunch of operators U of T which act on both the in and the out states. Now, let me remind you that this was an issue which we discussed in the last lecture as well. The in states and out states would definitely furnish representations of our transformation. In the last lecture, they were furnishing representations of Poisson transformations. In today's lecture, we are talking of representations of internal transformations. But it is not obvious that they are going to furnish the same representation. That is, the representation is going to be implemented by the same bunch of operators in the two cases. If the implementation is done by the same bunch of operators, that is, if we can do what I have just done, apply the same U of T on both the in and the out states, then and only then does this calculation work. But that is exactly what we mean when we say that the T's, all the internal symmetry operations together, actually are a symmetry of our system. This actually is my definition of what symmetry of a system means. If a particular system has a symmetry, then that symmetry must be implemented by the same unitary operator acting on the in states as well as the out states. The upshot of all this is the existence of an internal symmetry of a system imposes this particular restriction on the S matrix elements. And here I have deliberately put in green underlines below the n's everywhere to emphasize that it is only the n's which are affected or which combine linearly on their side because of the internal transformations. This is to once again emphasize the difference between this case and the previous case that we studied, that of Poincare transformations. For Poincare transformations, it was the p's and the sigmas which were affected by the transformation, and n's stayed aside as a spectator. Here it is the n's, the particle species labels, which are being affected. Let us now go on to take a look at what this means in terms of the S matrix. Let me remind you once again that the S matrix is defined via this relation, which tells you that the S matrix elements S alpha beta, which remember were nothing but psi alpha minus psi beta plus, the overlap between the outstate psi alpha and the in-state with labels beta is the same as the matrix element between the free particle states phi alpha and phi beta with the same respective particle labels of the scattering operator. Now, this is exactly the same relationship here. I've just written out the alpha and beta labels in more detail. So, alpha, the labels for the outgoing particle states, actually is a bunch of labels, not one. One label for each particle, P1 prime, sigma 1 prime, N1 prime, P2 prime, sigma 2 prime, N2 prime, etc. The prime signifying that we are talking about the out state, the detected state, and on this side you have the labels which make up beta, the in states, or the labels of the particles for the in states, P1 sigma 1 N1, P2 sigma 2 N2, and so on. As this equation tells you, this is nothing but the matrix element of the operator S, the scattering operator, between free particle states with the same particle labels as the in and the out states. Now, rather trivially, this is going to be equal to this expression, U0T phi P1 prime sigma 1 prime N1 prime P2 prime sigma 2 prime N2 prime on the left, and S U0T phi P1 sigma 1 N1 P2 sigma 2 N2 on the right, if something specifically happens. This will be true only if U0T actually induces on the free particle states phi with the outgoing particle labels here and the incoming particle labels here exactly the same transformation as U of t was applying on the in and the out states. In other words, the state phi P1 prime sigma 1 prime N1 prime P2 prime sigma 2 prime N2 prime acted upon by U0T is replaced by exactly the same linear combination of particle states, but this time free particle states with the labels N1 bar prime, N2 bar prime, and so on. And similarly for the states for the labels for the incoming particles. Before examining this equation further, let us just check whether this what I said right now is actually correct. The check is pretty simple. We are claiming that this is going to be correct, but notice that since U0T phi P1 prime sigma 1 prime N1 prime is basically this linear combination and U0T acting on phi P1 sigma 1 N1 is this linear combination and S is a linear operator, these coefficients, they come out of S and they come out of the inner product. So do these coefficients, but of course they come out as complex conjugates. And as a result, you end up with this expression. Now this exactly is the formula that we had highlighted a while ago. The restriction on the S matrix elements which come from the fact that you have an internal symmetry. Now, to understand exactly what this restriction means, let us go back to our original expression. We are claiming that this overlap is exactly the same as this particular overlap. That is equivalent to the symmetry restriction that we put on the S matrix elements a while ago. But because U0T is a unitary operator, you can move it to the other half of the inner product as U0 dagger or U0 inverse T and end up with this expression. Now, if these two expressions are to be equal, no matter what free particle states you have in the incoming side as well as the outgoing side, the only possible way in which that can happen is that this operator here, U0T inverse S U0T, must be the same as S. This is the same thing as saying that an operator U0T which induces the same transformation on free states, that is U0T acting on phi, produces the same combination of the free particle states as UT did on both the in and the out states, must end up commuting with S. This operator U0T's commutator with S must vanish, and for this to work, what we must have is U0T must commute with both H0 and the V, that is, with both the free particle Hamiltonian as well as the interaction term. Now, if this happens, of course, U0T is going to commute with both H0 and H, and it's easy to check that then it has to commute with S simply because S, remember, is a limit of this particular operator. It is a IH0 tau, it is a minus IH tau minus tau 0, it is a minus IH0 tau 0. As tau goes to plus infinity and tau 0 goes to minus infinity, if U0 capital T commutes with H0 and H, then it actually commutes with this operator irrespective of the value of tau and tau 0. So it commutes with the final limiting value of S. So S and U0T commute as we need it. Now what about the other important demand? The demand that we have for this at all to be a symmetry operation is that the same operator U of T must act on the in and the out states and produce this given transformation. Note that we are not demanding ab initio that U of T must be the same as the operator which acts on the free particle states. It's possible, at least at this stage, that U of T and U0T were different. Indeed, in the case of Poincare transformations, we did see that UT and U0T had to be different. After all, the time translation generator, which is a specific example of a Poincare generator, happened to be H0 for free particle states, and H would generate time translations on the in and out states. So here, let us take a look at what exactly is the relationship between UT and U0T and whether the condition that we have stated right now, that is, U0T commutes with both H0 and V, is sufficient to ensure that we can find a given U of T which will act on both the in states and the out states and produce the same transformation. In order to see this, we need to see how to get the in and out states out of free particle states, and that, remember, is done by the operators omega minus plus infinity, the Euler operators, where omega tau is defined to be e to the IH tau times e to the minus IH0 tau. Now, it's easy to see that if U0 capital T, the operator which implements the internal transformation, commutes with both H and H0, then it commutes with omega at every tau. Well, I have shown that explicitly here by writing out omega tau as e to the IH tau e to the minus IH0 tau, and then supplying an U0T, U0 inverse T in the middle, so that you can see that this term has to be equal to the IH tau and this term has to be equal to the minus IH0 tau, giving you back omega tau. So omega tau U0 capital T has to be U0 capital T omega tau. And therefore, U0 capital T commutes with omega for all tau values, and in particular it commutes with omega minus plus infinity. So notice that if you start with omega minus plus infinity acting on phi alpha and apply U0T on that, the result is the same as applying use t first on phi alpha, the free particle state, and then apply omega minus plus infinity. Now, this result here, omega minus plus infinity, acting on phi alpha, is nothing but the corresponding states psi plus or psi minus, the in or out states with the same particle labels as alpha. I've just expanded the particle labels out here and applied u0t on the left, which is exactly this expression. On the other side, we have omega minus plus infinity. Then u0t goes and acts on phi alpha. Remember, our claim is u0t will produce on phi alpha a linear combination which is given by the same coefficients as what we demand ut to do. But now, omega minus plus infinity acting on this whole combination will completely jump across all these numbers. These are of course matrix elements which are just numbers, and go and hit the phi. And omega minus plus infinity hitting the phi will of course give you the psi plus minus with these labels. So notice that here we have managed to get exactly the same transformation on the in and out states, but the operator that we needed for that is not a different operator. u0t actually does the same job on both the in and the out states as it did on the free particle states. So at least for internal transformations, we can actually find operators u of t which will do exactly the same job for both in states and out states, induce this particular transformation, and that's nothing but the same operator as the one which induces the transformation on free particle states. This is very different, of course, from the case with Poincare transformations, where the in and out states were acted upon by the same operators when a Poincare transformation took place, but this operator was different from the one which induced exactly the same transformation on free particle states. But ultimately what matters is that you have the same operator acting on the in states as well as the out states. That it happens to be the same as the one which does the job on free particle states makes life a bit easier here, but it wasn't really necessary to begin with for this to be a symmetry. So now that we have seen in some detail how an internal symmetry can be implemented on in or out states and what consequence that has on S matrix elements, let us take a look at a few simple applications of these ideas. Now, the symmetry transformations acting on a system form a group. That's well known. Now, we have also seen before that there is a special case which is of great importance. That is when the group happens to be a single parameter Lie group, where the elements capital T are labeled by a parameter. For Lie groups, they could be labeled by multiple parameters. But here we are talking of a single parameter Lie group. One single parameter theta is what labels the elements, and the composition rule then becomes very, very simple. T of theta bar times T of theta, where theta bar and theta are two different values of the parameter, is simply T of theta bar plus theta. Now, if this happens, then the corresponding unitary operator acting on the Hilbert space, U corresponding to T of theta, has this very simple form. It's e to the power I capital Q of theta, where capital Q is some operator, Hermitian operator, acting on the Hilbert space. Just to see how that comes about, let's point out that if this is true, then you can get to T of theta by just doing a transformation with parameter theta by n times. So you can take T of theta by n, repeat that n times, that is the same as raising it to the power n, and you will get T of theta. And because U's mimic the same multiplication rule that T's do, U of T of theta will also be U of T of theta by n raised to the power n. In particular, it will be equal to the limit of this quantity as n goes to infinity. But if n goes to infinity, then this parameter theta by n becomes infinitesimally small. So the corresponding unitary operator becomes something which is very, very close to the identity. After all, T of 0 would have given you the corresponding operator as identity. So get identity plus theta by n, which is the parameter for this case, times an operator which you call the generator. And I put in an I here, as we have already done before, to ensure that if capital Q is Hermitian if capital U is unitary. And it's easy to see that this particular limit is a familiar limit from high school algebra and gives you the exponential of IQ theta, this expression that we wrote down here. Now, in particular, we could choose a basis in which capital Q happens to be diagonal with eigenvalues Q1, Q2, Qn and so on. In that basis, the corresponding matrix elements Dn prime n corresponding to this T of theta will simply be diagonal, so it will have delta n prime n. It will vanish whenever n prime is not equal to n. And of course, the values will be e to the IQ1 theta, e to the IQ2 theta and so on. So, this is the expression that we have for Dn prime n. So, this is the case for any single parameter Lie group. The corresponding matrix elements will have this particular form. Now, if we put this particular form into our general expression for the way in which the S matrix elements behave when you have a internal symmetry, that is, it obeys this particular identity, then the following happens. Notice that what we have done here is we have replaced the T star n bar 1 prime n1 prime t, D star n bar 2 prime n2 prime t, etc. by these terms. Delta n1 bar prime n1 prime to the minus iq n1 prime theta. Then you have delta n2 bar prime n2 prime to the minus iq n2 prime theta and so on. So these are for the conjugations here. And for these terms, you will simply have delta n1 bar n1 to the iq n1 theta, delta n2 bar n2 to the iq n2 theta and so on. And finally, you have the S matrix element with n1 bar prime, n2 bar prime, etc., which are of course to be summed over. Now, because of the fact that your capital Q is diagonal in this basis, and so are the matrices curly D, we have these delta symbols here, the Kronecker delta symbols, which of course makes summing up over n1 bar prime, n2 bar prime absolutely trivial. And if we do that, all that's going to happen is all these n1 bar primes, n2 bar primes becomes n1 prime, n2 prime and so on. And similarly, the n1 bar, n2 bar here, which are being summed over from the incoming particle states, will also have to be replaced by n1, n2 and so on. So this is what you end up with ultimately. The S matrix element has to obey this condition. It's essentially the same S matrix element on the other side, because all the linear combinations have essentially degenerated to exactly one and only one value each. So n1 bar prime here has been replaced by n1 prime, n2 bar prime here has been replaced by n2 prime and so on. And this is the overall factor that we get from all these e to the minus iq theta terms. But if these are to be equal for all values of theta, then this factor has to be 1 for all values of theta. And that can only happen if the exponent vanishes. And therefore, we end up with a very, very important consequence. These eigenvalues of the Q operator must sum up to the same value for the final state as they did for the initial state. If they don't, the only possibility by which this equation leaves us is that S must vanish. So probability amplitude for a transition, which is what the S matrix elements are, will vanish unless this particular condition is obeyed. In other words, the total value of Q is conserved. So whenever you have an internal symmetry which can be implemented by a single parameter Lie group, the consequence is that you will have an additive conserved quantity, a quantity which can be just added together to get its value in the incoming side, and that must match the value on the outgoing side for the particular transition or particular transformation to take place. Of course, conservation laws are very, very important in physics, and here we see a very deep connection between that and internal symmetries. And some very familiar conservation laws are consequences of such internal symmetries. For example, the conservation of electrical charge that we all know of is something which follows from a very simple internal symmetry called the U1 symmetry. Well, in the world of elementary particles, things like baryon number, lepton number, strangeness, etc. are conserved, and each one of these conservation laws correspond to a one-parameter Lie group of its own. We will not go into the details of these conservation laws simply because that would take us too far away from our basic goal here. Also because these things are pretty familiar and you will find lots of details in any book which deals with elementary particle physics. One thing that I would like to point out though is that the electric charge is a conserved quantity for all known processes. We know of no exception whatsoever to this conservation law. Baryon number conservation, which is the conservation of the number of baryons, neutrons, protons, hyperons like the lambda particles, sigma or z particles, total number of these particles minus their antiparticles. This is a conserved quantity as far as we know. Again, no exception has been observed yet, but there is good theoretical reason to believe that there may be processes where baryon number conservation is violated. Although, frankly, that's still speculative in a sense. No baryon number conservation violating process has ever been observed. Similarly, lepton numbers, which is the number of electrons, muons, tauns, and neutrinos minus again the anti-electrons, that is positrons, anti-muons, and so on. This number is also conserved as far as all experimental evidence goes, and once again there is theoretical reason to believe that this may not be an exactly conserved number. In other words, the symmetry underlying the lepton number conservation may not be an exact symmetry. However, as far as experimental evidence till date goes, both of these are exactly conserved. There are no known exceptions, at least no observed exceptions till date. Strangeness is an entirely different story. Strangeness happens to be a conserved quantity for strong interactions, but it is violated in weak interactions. Indeed, the whole idea behind strangeness conservation came about because people observed that there were certain particles, the lambda 0 in particular, which actually was created very, very rapidly, indicating that it's being created by a strong interaction, but which decays only very, very slowly, indicating that it cannot decay via a strong interaction, decays only via a weak interaction. So this could be only explained by assuming that there is a conserved quantity called strangeness, which is conserved in strong interactions, and because lambda 0 happens to be the lightest strange particle, it could not decay in any process which conserves strangeness. On the other hand, it could decay via weak interactions because this particular conserved quantity is not really conserved under weak interactions. So the interaction Hamiltonian term for strong interactions do commute with the operator which induces the corresponding symmetry for which strangeness is a conserved quantity. But on the other hand, the interaction term for the weak interaction does not commute with this operator, allowing strangeness to be violated in weak interactions and therefore allowing the lambda 0 particle to decay via a comparatively slow weak interaction process. So what we notice here is that among the conserved quantities, there are exact conservation laws, there are laws which are exact as far as we know, and there are conservation laws which we know are not exact. Of course, one thing which is common between all the conservation laws here are they are all due to abelian symmetries. Symmetries caused by one parameter Lie groups, elements of which commute with each other. The next example that we are going to talk about is a classic example of a symmetry which is not completely a symmetry. It is a symmetry of the strong interactions. However, it is not a symmetry of electromagnetic interactions. And it also happens to be not an abelian symmetry. In fact, it's the classic non-abelian internal symmetry that we are going to discuss next, so-called isospin symmetry. This isospin or isotopic spin symmetry was originally proposed because it was found that the proton-proton strong force is very, very similar to the proton-neutron strong force. In fact, the proton and the neutron are very similar particles except for one very important property. The proton is charged and the neutron is not. So it's obvious that thinking of them as two states of the same system, same particle, the so-called nucleon, will not really make sense because any symmetry which conserves charge will of course not be able to mix the two particles with each other. On the other hand, if we for the time being forget about electromagnetism and concentrate only on the strong force, a symmetry operation which mixes the proton with the neutron states under an internal transformation can actually very well serve as a symmetry. And this is the symmetry that we talk of as isotropic spin. The corresponding symmetry group here is basically one whose fundamental representation mixes two states with each other. This is the group SU2 with generators T1, T2, T3 which actually satisfy a very, very familiar commutation relation. The commutator between Ti and Tj is I times epsilon ijk Tk. That is T1, T2's commutator is It3 and so on. This of course is exactly identical to the familiar commutation relation that we have for angular momentum operators, and there's a very big reason for that. While the group SU2 is not the same as the group of rotations, the group SO3, it happens to be the universal covering group of SO3. Now, if you do not know what that is right now, let's not worry too much about it. I did discuss this at length in my symmetries in physics course, but for the time being, all you really need to worry about is the fact that when you are stuck infinitesimally close to the identity, the behavior of these two groups are very, very similar, and that is why their generators, which talk about infinitesimal displacements away from the identity, obey the same commutation relation. Now, as I have stressed several times, this is an approximate symmetry. Had it been exact, it would have predicted the existence of a degenerate multiplets of particles with exactly the same mass, which essentially would be different states of the same particle, so to speak. The classic example that we started out with was, of course, the nucleon, whose two states would have been the proton and the neutron, which would have been identical had there been no electromagnetism. Indeed, the small difference in mass between the proton and the neutron can also be explained away by essentially thinking about this being an effect due to the electromagnetic interaction. Now, these multiplets would be labeled by integer or half-odd integer value, capital T. This is very familiar from the theory of angular momentum. It's essentially the same algebra being used here. Capital T is related to the eigenvalue of the operator T square, that is T1 square plus T2 square plus T3 square. And the very familiar result is the eigenvalue for T square operator is going to be capital T into capital T plus 1. Now, each of these multiplets will contain exactly 2T plus 1 particles, and each of these particles will be characterized by having different eigenvalues for the T3 operator. This eigenvalue, just called T3 without the hat on top, is going to label the different states of this superparticle, or will essentially give you each of these particles as separate identities. Now, examples, of course, the very first one is the one we started out with. For capital T equal to half, the number of particles in the multiplet will be 2T plus 1, and the very familiar example is small t3 equal to plus half will correspond to the proton, and small t equal to minus half will correspond to the neutron. Going forward, we have capital T equal to 1 multiplet, a triplet, where plus 1 corresponds to pi plus, 0 corresponds to pi 0, and minus 1 corresponds to pi minus, the 3 pions. Capital T equal to 0, an isospin scalar particle, is a singlet, the lambda 0 particle that we mentioned a while ago in the context of changes. One thing that you can see from these examples is that each of these T3 values correspond to different charges. In fact, when T3 changes by 1, the charge also changes by 1. Notice that in the proton-neutron doublet, the difference in T3 is plus half minus minus half, that's exactly 1, and that's the difference in charge between the proton and the neutron, and that actually also carries on to the other multiplets. So the T3 eigenvalue is related to the charge. However, it is not exactly equal to the charge. For example, in the proton-neutron doublet, the average charge is plus half. 1 for the proton, 0 for the neutron. And T3 essentially tells you how much the charge deviates from the average charge. So, if you take the average charge plus half for the proton-neutron doublet, add T3 equals plus half for the proton, you get the proton's charge, minus half for the neutron, you get the neutron's charge. Well, the average charge for the pion triplet is 0, and T3 values added to this average charge of 0, that is, the T3 value itself gives you the charge of the particular pion. The average charge of the singlet, the lambda 0 singlet, is of course 0. Now, twice the average charge of a multiplet goes by the name hypercharge, Y. And it turns out that this hypercharge is equal to the baryon number plus the strangeness of each and every particle of a multiplet. So, we end up with this formula, the so-called Gelman-Nishijima formula, Q equal to T3 plus B plus S by 2. And here, for the proton-neutron doublet, we can easily see that the hypercharge is twice 1 plus 0 by 2, that's of course 1, and that's consistent with the fact that the protons are baryons with a baryon number of 1 and they are not strange, so they have strangeness of 0. The pions are neither baryons nor strange, and therefore they have an hypercharge of 0, which is easily borne out by the fact that the average charge of the multiplet is also 0. The case with the lambda 0 hyperon is slightly different. It is a baryon, but it has a strangeness of minus 1. And therefore, B plus S, the hypercharge, turns out to be 0. And the average charge of the multiplet, which is half of that, is of course also 0. Now, this formula, although it was originally figured out empirically, actually hints at the existence of a bigger underlying group of transformations, which are symmetries of the system, or at least approximate symmetries of the system, where the operator T3 and the operator Y hat, which is the operator, which is the sum of the operators generating the transformation responsible for baryon number and strangeness conservation, these two are commuting generators of that particular larger group. So the elements of these multiplets, which are the particles which this model describes, are characterized by both T3 eigenvalues and the hypercharge eigenvalues. This is the so-called flavor SU3 model, which we perhaps know more familiarly as a quark model, the original 3-quark model. Indeed, although the isotopic spin symmetry was originally proposed as a symmetry which mixes protons and neutrons with each other, today we can think of that as a symmetry which mixes the up and the down quark with each other. And the fact that the up and the down quark are very, very similar in mass, although definitely not in charge, is responsible for the fact that you have approximate isotopic spin symmetry. Indeed, the fact that isospin symmetry is exact as far as strong interactions are concerned. Indeed, flavor SU3 can also be thought of as a consequence of the fact that the 3 light quarks, up, down and strange, happen to be very similar to each other. Not as similar as up and down, the strange is slightly different, which is why flavor SU3 symmetry is broken rather more badly than isotopic spin symmetry is. Now, the fact that isotopic spin symmetry is a symmetry for strong interactions has deeper consequences beyond just the existence of multiplets of nearly identical particles. It affects scattering processes in a rather rich and complicated way. Now, what makes our life a bit easy in this is that SU2, the underlying group for isospin symmetry, and our familiar rotation group SO3 have generators with the same algebra, and so we can use methods familiar from the application of rotational symmetry to figure out the consequence of isospin symmetry. For example, in the case of a two-body reaction where A and B react to produce C and D, A and B here are two elementary particles, C and D could be two different elementary particles, an immediate consequence of isospin symmetry on the scattering matrix elements happens to be the following. Here I have deliberately suppressed all other indices not pertaining to the particle species. The only particle species labels we have used for the outgoing states are the T3 values for the C and the D particles, and for the incoming state as the same T3 eigenvalues for A and B. Of course, S definitely depends on the momentum of the particles, the helicity states of the particles, and so on. We have just suppressed that information from here because these parameters are not very relevant as far as the action of the internal symmetry operation due to isospin is concerned. What isospin symmetry does here is that it puts us very severe restriction on the form of the scattering matrix element. As you can see, this scattering matrix element is now completely determined essentially by these numbers, which are familiar Clebsch-Gordon coefficients from the addition of angular momenta, and this one parameter St, which is a common parameter for all T3 values, depends only on the total isospin angular momentum, so capital T. And of course, what is suppressed here in this notation is that St depends not only on T but also on the momentum of the incoming particles and their helicities and so on, but they are in particular independent of the TA3, TB3 parameters which actually distinguish one particle from another. The Clebsch-Gordon coefficients are the familiar quantities which may have a used in a slightly different notation here. They are nothing but the coefficients of J1, M1, J2, M2. So J1, J2 are the two labels sitting here, TC, TD in this case, TA, TB in this case. And M1, M2 are the corresponding T3 eigenvalues. So this notation is basically the coefficient of J1, M1, J2, M2 in the expansion of J1, J2, Jm. Remember, these are eigenstates of basically the first particle's angular momentum squared, in this case isotopic spin angular momentum squared, J3 eigenvalue for the first particle, this is J2 square, and this is J3 eigenvalue for the second particle. Maybe I should write this as J2, 3. So this 2 stands for the second particle. This is the third component. On this side you have J1, J2 which mean the same thing as on this side. A Jm essentially is for the total angular momentum squared, in this case total isotopic spin angular momentum squared, and total J3 eigenvalue. So the important point here is we know these coefficients from the theory of angular momentum, and so we can severely restrict the form for scattering matrix elements from this result. And in particular, what is very important is, although this looks like a sum over all capital T and all T3, ultimately the Clebsch-Gordon coefficients vanish for nearly all capital T and T3, so this is a really small sum. In particular, the only T3 eigenvalue which is going to contribute here is the one in which T3 equals TA3 plus TB3, and this enforces that TC3 plus TD3 must be the same as TA3 plus TB3. Remember, the T3 is actually related to the charge and the hypercharge, and so this really is nothing new. This simply is an effect of the conservation of charge and hypercharge for strong interactions. But this means that although this formula looks like it has a rather large sum, it only has very small number of terms to worry about. Similarly, capital T is restricted to between the sum of TA and TB and the difference of TA and TB. Otherwise, this particular Clebsch-Gordon coefficient would vanish. A similar thing can be said about this particular Clebsch-Gordon coefficient, which ultimately means that for particular cases, this sum may be reduced to a very small number of terms, leading to very important observable predictions about the scattering matrix elements. Now, in Weinberg's book, he just goes and states this formula and does not really elaborate upon this at this stage. simply because he assumes that this is a familiar formula from the theory of angular momentum symmetry in quantum mechanics. And of course, his main thrust is not really in looking at individual applications. His main thrust is to look at the bigger picture. But I feel it's important that we understand this formula thoroughly. It will both give us a feel of how these particular symmetry arguments are really being used, and this particular formula actually leads to very important applications. So, breaking away with Weinberg, what I'm going to do in the next lecture, which will necessarily be a very short one, is give you a proof of this particular formula and also give examples of how to use this in the context of elementary particle physics. In fact, this last part is available in most elementary particle physics textbooks, especially the ones which deal with symmetries and their effects in elementary particle physics, but usually most textbooks use a slightly different notation as well as approach the problem in a slightly different manner. Weinberg's version, the form in which he has stated this particular equation, is interesting in its own right, so I will spend some time on that. But that will have to wait for the next lecture, which I hope to make very soon. In the meantime, let me point out that I have already discussed much of this topic in a slightly different notation in the context of rotations in quantum mechanics. The videos are somewhere in my channel, so if you want to look at those, you're most welcome. Bye then, till we meet again with the next lecture.